Welcome to the test review for Unit 3. Which of these is the electron configuration for calcium? You have to remember that calcium, first of all, is element number 20. So you're looking for one of these configurations that has 20 electrons. And then the second part is which of these has those 20 electrons in the right order. So choice A does not have 20 electrons. Choice B does have 20 electrons, but if you look here, you've got 2p and then 3d, which is not the correct order. And then D also has 20 electrons, but then you've got 4s and 3d without the 4s being full. There's only one there. So the choice here is C. That is the correct configuration for calcium. What is the electron configuration for the sulfur ion? S with a charge of -2. Well, first you have to remember that sulfur is element number 16, so its normal electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p4. That's what it would normally look like. But since we have this -2 charge here, that means that you have 2 extra electrons, 2 more than usual. So instead of 4, we have 3p6. 3p6 brings our total electrons from 16 to 18. And the element with 18 electrons is argon, and this is the only one of the choices that has the right number of electrons in the right order, or in this case just represented by the noble gas argon. The element aluminum tends to do what in order to become more stable? Well, aluminum is element number 13. It's a metal, and all metals tend to lose electrons, and aluminum is in group 13 as well as being element number 13. And remember, if you're looking at the group number for the elements in 13 through 18, you look at the second digit. So aluminum has 3 valence electrons that it wants to get rid of because its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So it has a choice to get to a noble gas. It can go up 5 more electrons and go get 5 more electrons to get up to 18 for argon, or it can shed or give away those 3 outer electrons, which would leave it looking like this, which is the configuration for neon. It's easier to get rid of 3 than it is to gain 5. So aluminum, all metals lose electron, and aluminum loses 3 electrons because it has 3 to give away. Which element matches the configuration 1s2, 2s2, 2p6? Or in this case, you've given 2 choices in each of these categories. So neon and argon, no, because neon has 10 electrons, which is what this has, but argon has 18. Neon only could be a choice. Let's look here though. Neon and sodium. Neon is 1s2, 2s2, 2p6. Sodium is normally 1s2, 2s2, 2p6, 3s1. But here it says you've got a +1 charge, which means it's gotten rid of one of its electrons, which leaves it looking just like neon. So the answer here is going to be C. It can't be magnesium. Magnesium would never have a +3 charge. But you've already identified neon and sodium as having the same configuration. What is the configuration for the magnesium atom? Well, magnesium is element number 12, so it would be 1s2, 2s2, 2p6, 3s2. Well, that's this choice, but this choice is also neon 3s2. That's actually the noble gas abbreviation for magnesium, because the neon represents the first 10 electrons, and then we add on the 3s2 to make it magnesium. So the correct answer here is C, because both A and B would represent magnesium. The element potassium has how many valence electrons? The number of valence electrons, you can either write out the configuration and then take a look at the highest energy level, or if your element is in one of what's called the representative groups, which when you're looking at the periodic table, it looks something like this. The elements here and the elements from here over are called the representative elements. And they have column numbers 1, 2, and then 13 through 18 at the end. All the elements in group 1 have one valence electron. Potassium is in that group. So it's going to be choice B here. Continuing on, so group 1, all elements have one valence electron. Group 2, they all have two valence electrons. In the groups 13 to 18 over here, you just look at the second digit. So 13 has 3, 18 has 8, 14, 15, 16, 17 have the corresponding numbers in between. Barium tends to form what type of charge? Well, barium is a metal. Okay, so that means it's going to be a positive charge. All the metals tend to form positive charges. How many valence electrons does barium have? Barium is in group 2, or column 2, so that means it has two valence electrons, which means it's going to lose, since it's a metal, two valence electrons, and that means the charge is going to end up being positive 2. Remember, you're losing a negative particle when you lose an electron, which means you end up with a positive charge. Which of the following is not isoelectronic with the others? Isoelectronic is just a fancy way of saying they have the same configuration. So 3 of these elements would look the same if you looked at the electron configurations. One of these things is not like the others. So we can do them out. Chlorine with a -1 charge, 1s2, 2s2, 2p6, 3s2. Normally chlorine would be 3p5, but since it has this -1 charge, it's got one extra electron, makes it 3p6. Alright, so argon is element 18, 1s2, 2s2, 2p6, 3s2, 3p6. So those two are the same. Oxygen with a -2 charge. Oxygen is element number 8. So if it has a -2 charge, it's got 2 extra electrons, which would be 10, 1s2, 2s2, 2p6 would be 10. So oxygen is not like these other elements, and argon is normally number 19, but since it's got a plus charge, that means you take away 1, 18 electrons, so it's going to look just like these other two. So the correct answer here, the one that's not like the others, is oxygen. All the elements in group 1 end with the configuration, well, again, if we draw our very simple drawing of the periodic table, remember the first two groups over here are called the S block. The groups over here are called the P block, the D elements here, and then if we had those extra 2 rows down here, those are called the F block elements. There are 2 columns in the S block, groups 1 and 2. Elements in group 1 have a configuration that ends with S1. In group 2, they end with S2. In the first column of the P block, they'd end with P1, and so on. So the end of the configuration is the letter of the block that they're in, S, P, D, or F, and then the number up at the top is which column in that group are they. So this would be P1, P2, P3, 4, 5, 6, S1, S2, and then this would be D1 through D10. Down here you've got F1 to F14. So back to the question. Group 1 elements have S1 as the end of their configuration. Elements in group 13. Well, we're looking at the periodic table again. Group 13 is right here, so it's in the P block, and 13 happens to be the first column in the P block, so those configurations are all going to end with P1. Alright, group 17 in the P block again, and group 17 is the row of, the column of elements that's just before the noble gases, so the next to last column in the P block, and it's 1, 2, 3, 4, 5, and the noble gases are group 6 in the P block. So group 17, which is called the halogens, have configurations that end with P5. The number of valence electrons for carbon is carbon, look on the periodic table, it's in group number 14. For valence electrons in the teens, we look at the second digit, so we're talking about 4 valence electrons. Beryllium is in group 2. This one's really easy. Group 2 elements have 2 valence electrons. Calcium is also in group 2, so it also has 2 valence electrons. The group numbers and the valence electrons go together. Which of the rules regarding electron configuration says that electrons always occupy the lowest energy orbitals? That is the building up principle, which is called the Aufbau principle. Pauli exclusion is the one that says the electrons have to spin in opposite directions. Hund's rule is the one that says you spread them out into different orbitals if you can. And Fall's rule, you'd have to ask Mr. Fall, but I'm sure it's hysterical. All right, number 16, all atoms gain or lose electrons to become like what? What configuration are they all trying to achieve? The most stable configuration is the configuration that all the noble gases have. So that's what they're all trying to get to. Which electrons are located in the last shell and determine how an atom bonds with other atoms? This is a specific group of elements called the valence electrons. Those are all the electrons on the outermost shell. Which element has the configuration neon 3s2 3p4? Well, neon is element number 10. So there's a couple ways you could do this. You could look at the number of electrons. Well, we've got 10 plus 2 plus 4, which means we're talking about element number 16. Or you could look at the fact that it's 3p4. So the 3 tells you it's in the third row of the periodic table if you're looking down at the periodic table. The p tells you that it's in the p block over here, and the 4 tells you that it's the fourth column over in the p block, which would put it right here, and that element is sulfur if you find it on the periodic table. Which element has the configuration 4s2 3d3 following argon? Again, different ways to do it. Argon is 18. 18 plus 2 plus 3 is 23. It's also 3d3, which means it's the third column over in that middle D block. So the D block is the one in here, so you'd count 1, 2, 3 over, and you'd find that that is vanadium. All right, we've got xenon, 6s2 4f3. This is the first time we've seen the F block on here. So the F block is the 2 rows at the bottom of the periodic table that are always kind of down here by themselves. 4f is the first of those 2 rows, and 4f3 means you're going to go 1, 2, 3 over, and that's where you'd find praseodymium. And then the configuration radon, 7s1. 7 means 7th row, S means S block, and 1 means first column. S1 is the very first column of the periodic table, way over here. 7s1 happens to be the very last row, and that element, 7s1, the very bottom left of the periodic table, is francium. 4s1 3d10. This is a tricky one. I wouldn't give it to you like this on the actual test, because if you look closely, this configuration is actually not correct for a ground state element, because it's 4s1 3d10. So depending on what you did here, you might have thought, well, the correct answer isn't here because 3d10 is zinc, and that's not one of the choices. But if you notice that the number is off, you'd notice that this is 1 less than it should be, and the answer in that case would be copper. Elements on the left side of the periodic table tend to be metal elements. Left-hand side of the periodic table is all metals, and metals always lose electrons. The right side of the periodic table is where you have the nonmetals, and all the nonmetals tend to gain electrons. 2 properties of electromagnetic spectrum are frequency and wavelength. Those are the 2 things that we can use to find other measurements. The longer the wavelength of a wave, the higher, lower, shorter, or longer the frequency. Well, if you remember that the frequency is the number of waves that pass by in a given amount of time, and then you think about a wave that's longer, well, longer waves are going to take longer to get through, which means there's going to be less of them. And also you have to remember that wavelength and frequency are what are called inverse, which means if one goes up, the other goes down. So long wavelength means low frequency. Radiation with the highest frequency and energy go together. They go in the same direction. There's a direct relationship. The highest energy form of electromagnetic radiation is gamma rays or gamma waves. If you were talking other than in rank, this would be next. So the correct answer is D. So this would be the highest, this would be next, this would be third, and radio waves would be fourth. Which color of light would have the greatest amount of energy per photon? Well, the energy, if you look at the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet. the energy goes from lowest is red to highest is violet. And of these choices, the one closest to violet is blue. So that would be the one with the highest energy. If an electron falls from third to second energy level and gives off violet light, and then it falls from the third to the first level, what kind of energy would it give off? Well, violet is the highest part of the visible spectrum, and that's what you got when you got one from 3 to 2. 3 to 1 would give off even more energy because there's a bigger difference. So radio waves, infrared, and blue light are all below violet on the energy spectrum. So ultraviolet, which is just beyond what we can see on the higher end, would be the highest energy of these choices, and that would be the one to go with. How many bonds does an atom of nitrogen want to form? The number of bonds an atom wants to form is related to how many electrons it's either going to gain or lose. So nitrogen is in group 15, which means it has 5 valence electrons. Since it has 5, it's a nonmetal, it wants to gain 3 electrons to get to 8, right? Because that's what all the elements want. Well, in order to gain those 3 electrons, it's going to have to form 3 bonds with other elements, either 3 with one element, or 2 with one element, or one atom, and 1 with another, or 3 individual bonds. We'll get more into the different types of bonds and how you can have single, double, or triple bonds. But for right now, the number of bonds is the number of electrons it's going to gain or lose. Nonmetals gain electrons. This one's going to gain 3 because it needs to get from 5 to 8. So it's going to form 3 bonds in order to do that. Okay, some wavelength, frequency, energy questions. So calculate the frequency of a photon traveling with a wavelength of 530 nanometers. So the trick when it's given to you in nanometers is to remember that 1 nanometer equals 10 to the negative 9th meters. So what I'm going to do is, for any time you're calculating frequency with wavelength or wavelength with frequency, you use the speed of light, which is 3.00 times 10 to the 8th, and you divide it by either the wavelength or the frequency. The trick is you want the wavelength, you want the wavelength to be in meters when you're doing the math. But the easy thing is, when you're talking about nanometers, you can just say 530 times 10 to the negative 9th meters, and that converts it from meters to nanometers just by putting the 10 to the negative 9th there. So when I do that out, I end up with 5.66 times 10 to the 14th hertz. And just a reminder, as always, if you have your calculator and you don't know how to do the scientific notation in your calculator, please come see me and we'll practice how to do that. Because if you can do that with your calculator, it will save a lot of trouble and make it much more likely for you to get the correct final answer than trying to do some of this in your head or in multiple steps. All right, number 32. What is the energy of a photon with a frequency of 5.3 times 10 to the 20th hertz? Remember, the energy equals Planck's constant times the frequency. So, and Planck's constant is 6.626 times 10 to the negative 34th power. And we're multiplying that by the frequency of 5.3 times 10 to the 20th power. And we get an answer of 3.51 times 10 to the negative 9th. And the unit for energy is joules, with a capital J for the abbreviation. Calculate the energy of violet light with a wavelength of 4.2 times 10 to the negative 7th meters. So what they did here was they're asking for energy, but they didn't give us the frequency. They gave us the wavelength. So we have to go back to wavelength times frequency equals speed of light. We can use the wavelength to find the energy, to find the frequency, and then we can use the frequency to find the energy. So step 1 is 3.0 times 10 to the 8th divided by the wavelength, 4.20 times 10 to the negative 7th meters. That gives us an answer of 7.14 times 10 to the 14th hertz. And then we multiply that by the 6.626 times 10 to the negative 34th Planck's constant. And that gives us an answer of 4.73 times 10 to the negative 19th joules for energy. So 2 steps when you've got wavelength and you want energy, you first have to do the 3.0 times 10 to the 8th divided by the wavelength. Take that answer and multiply it by the 6.626 times 10 to the negative 34th. All right, what is the electron configuration for the atom shown below? Well, you have to count up the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 electrons. 1s2, 2s2, 2p6, that's 10. 3s2 is 12, and then I need 3 more, so 3p3. So that'd be the electron configuration. 15 electrons, the order 1s, 2s, 2p, 3s, 3p, and that's as far as I needed to go. What is the element symbol for this atom? Well, element number 15 is phosphorus, so that would have a P for the symbol. What type of charge does this atom want to form? Well, phosphorus is a nonmetal, which means it's going to gain electrons. Right? Nonmetals all gain. And when you gain electrons, it's going to have a negative charge, and it has 5 valence electrons, which means it needs 3 more to get to 8. So its charge is going to be -3 when it forms an ion. And which noble gas is this element going to try to become? Well, it's element number 15. The 2 elements on either side of it would be neon at number 10 or argon at number 18. It's 3 away from argon, it's 5 away from neon. So the easier choice is going to be to end up with a configuration like argon. So that's the answer. What is the process that causes atoms to emit light according to Bohr's model? And include a diagram. All right, so if we have an atom with a nucleus, and we have orbits, according to Bohr's model, if you have electrons, I'll say that's an electron, an atom can absorb energy from the outside, and the electron can take that energy and use it to jump from one orbit to another. And then when it returns back to its original state, to its original ground state, it has to give that energy back. So to get back down to the ground state, it has to give away the energy, and it gives the energy away in the form of light. Now the type of light we get depends on the energy jump. So for example, blue light would be from a bigger jump, green light would be from a slightly smaller jump, and then maybe you get yellow from an even smaller one. Or red, for example. Red would come from an even smaller jump because that's a lower energy. So the color of light you get is dependent on how far the electron is going, because the farther it goes, the more energy it's giving back, and it always gives back the energy in the form of light. The color of light is dependent on how far that electron is dropping down. Small jumps give you red, orange, yellow. Bigger jumps go to green, and then blue, indigo, and violet. And that's how you get the different colors of light. Iron can form either a +2 or +3 ions. Which elements are lost in order to form each ion? Use an orbital diagram. All right, well, I'm going to use sort of a hybrid electron configuration and orbital diagram, because we're really looking at the valence electrons here. So 1s2, 2s2, 2p6, 3s2, 3p6, and then I'm going to switch over. So it would be 4s2, and then the next is 3d6. Okay, if you do that out, because iron is element number 26. So it's element number 26. So there's 26 electrons. Well, when it forms a +2 ion, that means it's lost 2 electrons. So the 2 electrons it's going to lose, like all other metals, are the 2 electrons on the outermost energy level. Even though 3d comes after 4s, the 4 is the highest energy level, so those are the first to go. Okay, so that's when it forms a +2. It just gets rid of those 2 electrons on the 4th level. Now, when I do this again, I'm going to just use the noble gas abbreviation to make this a little quicker. 4s2 and then 1, 2, 3, 4. There are 6 electrons in the 3D level. In order to get that +3 charge, it has to lose 3 electrons. Which ones is it going to lose? Well, it loses these 2 first. Now, which one might be the next one to go? Well, if you remember the rules for electron configurations, electrons don't want to share an orbital. They would rather be by themselves. So the next electron to go is going to be one of these 2 electrons in that doubled up 3D orbital. Because now, and I'm just going to erase this, now you've got 5 orbitals, 5 electrons. So because those 2 electrons were in that first orbital together, they were pushing each other away a little bit. So that's the next one to go. After the first 2 in the 4s, the next one to go is the extra one in that 3D orbital. Make a graph of energy versus wavelength and energy versus frequency. Well, energy versus wavelength, the longer the wavelength, the lower the frequency, and the lower the frequency, the lower the energy. So as wavelength increases, energy decreases. So it looks something like that. That's called an inverse relationship. It's got a negative slope. If I'm going to do energy with frequency, they go up. As frequency goes up, energy goes up. That's a direct relationship, a positive slope. So that's really all you need to do there. And what is the constant represented by the slope of energy and frequency? Well, energy times frequency, or energy and frequency, the slope is Planck's constant. That's the number we use to find the energy if we have the frequency. Planck's constant, which is represented by the letter h, and the number 6.626 times 10 to the negative 34th. So there you go. Make sure you know your electron configurations, how to find valence electrons, orbital diagrams and configurations for both neutral atoms and ions, all these frequency and energy calculations, wavelength, frequency, and energy, and have an understanding of the Bohr model and what that represents. Dropping from one energy level to another produces photons of light at different colors. The more energy, the higher the color is on the rainbow, from red at the bottom to blue at the top, and then ultraviolet above that, infrared is below that. And that should do it. We'll see you soon. Come see me Monday if you have any questions. Make sure you bring your calculator, and if you need to help with the scientific notation, be sure to come ask me before the test starts.